In this slidecast, we're going to discuss testing programs. Even after all syntax and runtime errors are removed, if a program executes through to normal completion, there still could be undetected errors. Now, the best kind of logic error is one that occurs in an area of the program that's always runs, and the worst kind is in an obscure part of the code that is executed infrequently. Now, that may sound backwards to you, that no, we don't want errors to happen, but this is from the standpoint of testing. It's really nice if something consistently fails. That helps us track it down. It's very difficult when we have a problem that rarely occurs. That's much harder to find and resolve. Now, most logic errors surface during the design phase, and they're the result of incorrect algorithms. We might have typos that might cause syntax or runtime errors. If we carefully check an algorithm before implementing, it helps avoid some of these errors. And then after implementing, we can hand trace the algorithm and simulate the execution and try to see if the results we get are what we expect. A structured walkthrough is when the designer explains an algorithm or a program to other team members and simulates its execution with the other team members looking on. And this can help the designer avoid overlooking a problem because they over-anticipated the steps it should do. Testing is the process of exercising a program under some controlled conditions to verify the results are correct. And the more thorough we can test, maybe the greater likelihood that we've found all the defects. But sometimes the number of test cases to test all possible inputs and states in a really complex program are just too large for us to actually accomplish. So it's impossible to guarantee the absence of all defects in such a program. So this is considering the case where we sort of brute force and kind of brute force sort of a test of a program. There are areas of computer science where people are working hard on ways to formally prove program correctness, and we're making progress in that area. But most software today is tested using test cases and the kind of testing we're talking about in this chapter today. So we've discussed earlier the different kinds of testing. We have unit testing, which is at the sort of the smallest level. We have integration testing to test the interaction among units. System testing is the whole program in the context it's going to be used. Sometimes a program will work correctly until some other software is loaded onto the system. And then acceptance testing is the system testing designed to show that the program meets its functional requirements. We want to use this system in as realistic an environment as possible. Now, there's two types of testing. One is called black box testing, or closed box testing, or functional testing. And here we test functions, classes, or programs just based on the interfaces and the functional requirements. This assumes that the tester doesn't know the details, the underlying details of how something is implemented. And it's nice to have someone with kind of that independent mindset come and try to test a piece of software. So we can vary the input parameters over the allowed range, and the results are compared against independently calculated results. And input parameters outside the allow range are tested to make sure the function responds as it should. The values of data fields and global variables can also be used in testing. Now, white box testing, it's called glass box or open box or coverage testing. It tests the same software elements, but this time we have knowledge of the internal structure. And this goal is to exercise as many possible paths through the software as is practical. And in white box testing, we might do statement coverage. This is very simple to make sure that every statement is executed at least once. And then branch coverage, this ensures that when we have choices in the software, when we have an if statement or a switch statement or loops, that all possible if statements must be tested with both a true and a false condition. And going even further, path coverage, we want to test every possible path through a function. By that, assume we have n if statements in a function and they're not nested. They just occur one after the other. So at each if statement, we have two possible choices. Okay, we could go A or B. Let's think 0 or 1. So if we've got n if statements, then there are 2 to the n possible paths through this code. So that can quickly grow to a large amount if we have a lot of conditional statements in our software. So here's a small test function. It accepts 2 characters as input parameters. And then we have some conditional expressions. If A is less than M and B is less than X, then we we set equal to path 1. Otherwise, we're at path 2. Else, we do some other checking. There's a path 3 and path 4. So we've got 4 different paths through this single if statement. And notice here's a table that shows for certain values of A and B, we'll take path 1, path 2, correct to path 4. So these are just using sort of the smallest and largest capital letters. So these are the uppercase letters. So what would happen if we, when A and B are passed values that are between A and Z? Also think about what happens when A and B are values that are not uppercase letters. Like what message would be displayed if A and B both had the string, the character 2, or if they both had lowercase letters? What if A were a digit and B is a lowercase letter? Now, to answer these questions, if you don't know the answer already, go look up the ASCII representation of these upper, lowercase, and digits, and see these comparisons are going to be comparing the ASCII value. So it may not be what you expect if you think of how we might normally order strings yourself. So the number of test cases, even for this simple function, can grow quite large quickly. Now, the earlier we can detect an error, the easier and less expensive it is to correct it. So a test plan should be developed early on in the design stage, and some aspects of the test plan could be deciding how you're going to test the software, when, who, and what is involved in the testing. And if the test plan is developed early in the design, then testing can happen concurrently with the design and coding. So if we're testing early, that encourages programmers to practice defensive programming, because they're preparing for tests to be happening very soon, not at the end after the whole system's been developed. So for example, if a function has a precondition that n is greater than 0, then the programmer can place an assert statement. We'll talk about this a little bit later, but this just basically has the program code checks and verifies that the precondition is met. And this assert macro can have a diagnostic message and can terminate the program when that precondition isn't satisfied. So the programmer can get a very clear message of where an error occurred and what was the problem. If a data value being read from a keyboard, if it's supposed to be between 0 and 40, then a defensive programmer might read this value and create this modified version of our read int routine. And this time the first parameter is going to be the prompt string, and then we'll pass in parameters for the lower and the upper limit. And then assuming we read an integer and there's not an error, so that the user did type in digits, we can do a further verification to verify whether this value is in the range low to high before we return it. And if not, then we can provide an error message and prompt the user again. So here's an example of that function call to this new read int routine that verifies that the number of hours worked is between 0 and 40. Now we should plan for testing as we write each module rather than after the fact. So here's 5 tips to follow when you're writing class definitions. So if the function implements an interface, then the interface specification should document the input parameters and the expected results. And you can document each parameter and class attribute carefully and use comments in the code and describe the function operation using documentation comments following the conventions in section 1.3. That's the things for Java Docs or Doxygen. You can leave a trace of execution by displaying the function name as you enter the function. You can display the values of all the input parameters, any important class attributes that you access in the function. When you exit the function, you can output the return values. And then you can check that these inputs and outputs are correct. Now here's a suggestion that I've seen done before, even in some moderately sized software systems. You could declare a static const variable called testing and set it equal to true, and then have an if statement around any of this testing output code that was suggested in the last slide. And the advantage of this is during the testing phase you can set this variable to be true, and all of this debugging testing kind of output will be generated. And then when you're done with the testing phase and maybe you don't want to be overwhelmed with all this data while you run the code, you can set this equal to false, and that just turns off the output. Now I've seen another strategy I've seen people do is to use compiler flags and for conditional compilation, so that you can compile in this output, and then you can set the compiler flag to be false, and then all of this output code won't even be generated by the compiler. So that was just a slightly more efficient way of doing it for a system that I worked on where they wanted very high performance when they were out of test mode. So you can have different Boolean flags for different kinds of tests. Or a system I worked on in industry, we had different levels of debugging. So depending on the level, you could get just occasional kind of general output, or you could up the level and get very detailed, dense output and information. The test data should be specified during the analysis and design phase, at the unit, integration, and system level. Now in black box testing, we want to focus on the relationship between the unit inputs and outputs. Check for all expected inputs, check for unanticipated data, develop a test plan to specify the expected unit behavior and output for each set of input data. Now in white box testing, we want to focus on exercising alternative paths through the code. And we design test data to ensure that all the if conditions will evaluate to both true and false, and then test different combinations of true and false if we have nested if statements. And make sure the selector variables for switch statements can take on all the values listed in the case labels and some that are not. Verify that loops are correct, an immediate exit occurs, 0 repetitions or just 1 repetition or the maximum number of iterations, and verify that the loop repetition can always terminate. Now here's a list of boundary conditions if we wanted to test this code. So let's look at this for statement. I starts at 0, and as long as it's less than x dot length, it's just incremented during each iteration. And then if the element of array x is equal to some target, then we return I. So this looks like a function that's searching for a value in an array. So if we want to thoroughly test this routine, here's some suggestions for you. We might want to find when the target element is the first array element. We can also test when the target element is only in the last element of the array, when it's maybe not in the array, or if there's multiple occurrences of it in the array, or if it's somewhere in the middle of the array. So we would like to test several cases where the target occurs at different places in the array, right at the beginning, right at the end, and a few other cases. We don't necessarily need to exhaustively test every condition, because for very large arrays we can assume that if we can find it in the middle, and if we find it at both ends, then that's a reasonable indication that that we've got maybe a correct search algorithm. The other thing we can do is we can test for exceptional cases of the array size. So what if the array has only one element in it? Or what if the array has no elements? We've got to make sure that something isn't broken on those maybe unexpected conditions. So in this case, the first 4 of these test cases are boundary conditions for the loop and they'd be required in white box testing, but also should be tested in black box testing. This test case where for the middle of the array, it's not a boundary case, but it's a typical situation. Usually we'd find something not at the extreme edges of the array, so it should be tested. And then these boundary conditions for the array search could be tested in white box or black box testing an array of maybe an unusually small size. So here's this code to search an array to find the first occurrence of the target character. Here's the for loop we saw on the previous slide. So here is a program to test this search routine. And we've got a main function, and we're first going to declare an array relatively small, and we'll put a set of values in that array, and that's the array we're going to search. And then we have a number of calls to this verify routine. And the verify routine is implemented here, and the verify routine takes the array x as a parameter and its length, and then it takes in a target value, the value we're going to search for, and then the expected location where we will find it. So with this small array, you can look through here and see that, well, 5 we should find at position 0, 7 we should find at position 6, that's the last element of the array, -5 doesn't occur in the array, and so forth. So we're testing, we're having one call to verify to test each of those cases we identified earlier. Here we have a one element array, and then here's an empty array. So here are all these cases that we had before. We'll call the same verify routine each time, and the verify routine calls search to get the actual result, and then outputs that result along with what was expected, and then with either the text pass if we got what we expected, or else failure if we didn't get what was expected. So if we run this program, and it runs as we would, if assuming search is implemented correctly, then all the test cases will pass. So I think this is an excellent example to give you an idea of how you can test your programs for this course. You can write a small test routine, come up with some test cases with a kind of routine that will check, and if you get the expected result, it will simply indicate pass. And once you've coded this up, then you don't have to sit and yourself examine the results and decide whether it passed or failed. It automatically determines that. So you can run this once, and then if any of these fail, that immediately gives you an idea of where to go and fix your code. And once you have everything working, if you come back later to make changes to the code, you can run the test cases again and make sure you didn't break something that was passing before. So who does the testing? Well, the programmer can do the testing. Other members of the team who didn't write the code, it's useful to have someone to not just rely on the programmer, but to have other people who aren't blind or biased because they're sort of so close to the code that whatever they didn't think of to include in the code the first time, they might not think of when they go to design some test cases. And you can have the final users of the software product. It's nice to have maybe non-technical people or someone independent of those developing the software, and they can look at all of the interfaces and the things that are prompted to the users to see if these things are easy to understand and appropriate. Companies often have quality assurance or QA organizations that verify that the testing process is performed correctly. Now, generally the programmer who wrote the unit does unit testing, but other people do the other kinds of testing. There's something called extreme programming that puts programmers in pairs. One writes the code, one writes the tests, and the tester observes the coder while the code's being written. And then they can take turns and change roles so that they can both be involved in coding and testing. Now, the substitute for a function that has not yet been implemented or tested is called a stub. So stubs are useful in testing when not all functions and classes are completed at the same time. Remember back to our model for software development, we said that testing starts early on in the development of the system. So how could we do that if we don't have the full thing implemented? Well, stubs help us do that. So a stub has the same header as the function it replaces, but the body is merely displays a message indicating that the stub was called. So we basically have a function implemented, and it doesn't have its final implementation. It has something much simpler. And this is one example of sort of the simplest function we might have. We could do other strategies. So the stub could also display the values of inputs and assign predictable values to any outputs, or predictably change the state of a data field if that's required. So here's a function to save the directory. So in our telephone directory program from Chapter 1, we need to output the data, the phone directory, to disk. And so we'll have this save function that will do that, and it returns, does not have any return value. And initially, if we're writing another program that wants to call save, we can have this stub where when we call save, it simply outputs, here's the stub for save has been called. And if we assume that we call save when a modified bit is true, then once we've saved the directory, this routine could set modified back to false. So here's just a stub. It's kind of a placeholder for the eventual routine that would actually output it to disk. But another programmer can be writing the other parts of the system and can assume there's going to be this save function, and so that code can compile and be tested even before we actually have implemented the save function. So this is the concept of a stub, and you can do that in the programs that you're developing. Once you've gotten a lab and decided on the various components, you can start building one component and have stubs for the other components, and to do some early testing of your system. A driver program declares necessary object instances and variables, assigns values to any of the function's inputs, calls the function, displays the values of any outputs returned by the function. The previous listing was a driver program to test the function search. And you should write driver programs for your labs, and there will be times where one of the requirements to pass off will be to develop your driver program and come and show that to the TA. Now, directory entry was a class from section 1.6, and the main function of this class could be considered a test driver. We could write test cases to verify that the constructor and the functions performed correctly. So here's some outputs that could come from that program functioning as a test driver. So a test case is an individual test. A collection of test cases we call a test suite. A program that executes this series of tests and reports the results is referred to as a test harness. A test framework is a software product that facilitates writing test cases, organizing them into test suites, running the test suite, and reporting the results. And there's an open source test framework for C++ that's called CPP Unit. Now, once we have our test plan and our test suite, the stubs and drivers and test results, we can save this, and then whenever we make a change to a function or a class or the program, then the tests, we can rerun them again to make sure we didn't have some unexpected consequence. And this rerunning and verifying is called regression testing. So in industry, when software products are released and you have a large test framework, then as you create future versions and modifications to this product, it's very common to do regression testing to make sure you haven't broken the things that were working earlier. Integration testing is where the program tester determines if the individual components, when they've been unit tested, we can see if we can integrate them with other components. And as we go through the phases of testing, we start getting larger and larger collections of software together until we finally have the entire system. Then integration testing determines whether the system is compatible with other systems in the computing environment. And if we've prepared UML diagrams as a system documentation, we can use those diagrams to determine the expected interaction between units in the system. And that brings us to the end of this slidecast.